Let's look at particles and waves, and this time at the photoelectric effect. So we know that light is an electromagnetic wave. When beams of light pass through a double slit, those waves will interfere with one another and produce an interference pattern, and that is the most telling thing that light is an electromagnetic wave. Now, experiments have shown that light also is composed of discrete particle-like entities, and those particles are now called photons. And one of these experiments is called the photoelectric effect. This photoelectric effect was first observed by Heinrich Hertz, and then it was explained by Albert Einstein. It turns out that even though we know Einstein for his theory of relativity, he won the Nobel Prize in Physics for the photoelectric effect in 1921. So what Einstein did was he proposed that light contains little packets of energy called the photons, and each one of those photons has energy hf, which is consistent with what Max Planck noticed, that energy was a quantized number, so an integer multiple of h, which is the Planck constant, and the frequency. So energy and frequency are directly proportional, and the proportionality constant is now called the Planck's constant. Now, what does this photoelectric effect tell us? It says that light of sufficiently high frequency shines on a metal. It can transfer its energy to an electron in the metal. So notice here that we said that light of sufficiently high frequency. It turns out that the intensity of the beam of light did not change the amount of energy that it transferred to the electron in the metal. There are three cases for this. The first one is that if the photon energy is too small, really nothing happens. If the photon energy matches the work necessary to eject an electron from the metal, then the electron will be released from that metal. Then if the photon energy is higher than the work necessary to eject the electron, then not only is the electron ejected from the metal, but it will also acquire a kinetic energy. So here is a little drawing of this. Let's say that we have a photon, and the photon is always symbolized as a squiggly line, and gamma stands for photon. So this is the photon striking a metal surface, and if there is an electron in here that is bound to the metal by something that we call a work function, so the work function is W naught, and if the energy that the photon has is h times f, according to Einstein, then if this energy is directly matching this work function, then the electron here will be released. Now, if that energy is larger than the work function, the electron will even acquire a kinetic energy. So by conservation of energy, we'll say that the incident photon, so this guy, will provide enough energy to release the electron and then give it some kinetic energy. So conservation of energy would look like this. E incident photon is equal to kinetic energy of the electron plus the work function necessary to release the electron. Or h times f is work function plus kinetic energy. So here is the expression for the photoelectric effect. And as somebody I knew once would ask, why do we care? Well, we care because nowadays we all like to do things like this. Take pictures, and we're using digital cameras nowadays to take the pictures. And all digital cameras use the photoelectric effect to capture the photos and store them in the cameras.